Okay, hi everyone. My name is Michael, and I'm from ICFO in Barcelona, where I build and use optically pumped magnetometers. This talk today is about making atomic sensors mass producible, specifically OPMs for biomagnetic studies and MEG. As we've heard in the other talks from this meeting, these seem to be the future of MEG. Since they're flexible, they're uncooled, they can be used closer to the body compared to conventional sensors like squids. So I'll talk about our approach to that, and we'll present two main results: some work on mass production MEMS vapor cells and some miniaturized coils for OPMs. And these results were obtained during the quantum flagship project Maximal, which is where we partnered with these other European institutes, the CSEM in Switzerland and MEG in VTT and ALTO in Finland. To start with then, well, when I say mass production, what sort of numbers could we be talking about? Well, even at the research stage, then we're thinking about, say, thousands to tens of thousands of units of OPMs, because we want lots of MEGs, and each MEG may have, say, 100 OPMs on it for full head coverage. And that's a big challenge if you think about making anything on that at that scale, especially if it's a very precise sensor, because for those sorts of numbers, we're asking for really reliable fabrication. So in other words, high yield, low wastage, really robust technology, and certainly rapid and automated assembly, and of course, low cost. And in addition, then OPMs need to be compact and lightweight, so that brings an additional challenge of miniaturization. So the good news is that the size challenge is somewhat solved already, because we've got simple approaches like the zero field resonance OPM. So it's got only a few parts. You have a light source, you have some optics to circularly polarize the beam, you have the vapor cell and a photodetector. And you can use a VCSEL, which is small and generally provides a sufficient amount of light. Just as a reminder then, that technique involves detecting the transmission of light through the atomic vapor, and that changes because of field-dependent absorption, like the one shown in this movie, which is showing an intensity modulation of the beam after the cell because of a modulated magnetic field, which is applied to the atoms using some coils. And as you may know, then typically we use sign modulation, demodulation of that magnetic field on the order of the absorption line width to obtain the demodulation signal. And we want the central slope of this curve to be as steep as possible to maximize our field sensitivity. And we know that there are several prototypes of this zero field OPM that have been made over the years, and some production units have been made too. To some extent, these are mass producible, so the Q-spin is maybe the most well-known at the moment. There are already groups trialing these for MEG with full head coverage. But certainly, these question marks remain unchecked, so unit cost for one is very high. And integration seems to be a bit lacking too, at least compared to other types of atomic sensor, like an atomic vapor clock. So I mentioned that because if you look at clocks, for example, this miniature clock or MAC developed mostly by Sandia, then the physics package is really, really highly integrated. So you just look here, for a start, it's this tiny PCB surface mount. So on that, there's this really tiny MEMS vapor cell here in blue. It's really millimeter scale. And then through that, then there's a beam, and this is a dual pass beam, because they actually put the light source and the detector on the same piece of silicon, shown here at the bottom. So that's really high integration, a lot of fancy fabrication that's used. And of course, this is a problem of scale mostly. Many more people are interested in precise timekeeping than magnetometry. So it's a question of affordability. But say it's a role model for future MEG with OPMs, then maybe we should be looking at clocks, especially because when we just look very schematically like this, then atomic clock and OPM have very similar hardware. So it's just a light source, some beam conditioning, the vapor cell, and a detector. So that's to say, maybe if you're an engineer rather than a physicist, then the clocks and the magnetometers are not so different from one another. So for our own starting point towards mass-produced OPMs, that was an inspiration for us, and it led us to working with CSEM and VTT. So they previously produced this clock package for Aurelia. This is called the MRO50 clock, and they made this fingernail-sized clock version using a MEMS vapor cell technology. So they put that together with the vapor cell shown here on the coin, and they put that together in this ultra flat package which a pick and place machine could assemble. So it's based highly on lithographic technologies, and the idea was to take the lessons learned from this high TRL and microfabricated design for us to build an OPM. There are some obvious differences, of course. So in the magnetometer, you have to arrange the components a little bit. For example, you want to keep the cell close to the package edge, as close as possible to the magnetic source. And you also want to keep the cell away from noisy components in the device, like the electronics. And also, light intensity losses tend to be more critical in the OPM. So beam delivery is important. And so you may want to choose a different strategy there, and that also includes avoiding beam noise, including intensity or polarization noise. And thirdly, then we also have very different cell characteristics. For magnetometry, we need to optimize those for the surf regime. So for the rubidium cells, we had a small production run made by CSEM. The manufacture of these cells was all done robotically using a process patented by CSEM for the MAC. It uses regular anodic bonding. As you can see here in this schematic, it's all done on a silicon wafer. So you start by etching, making half the cell, then you dispense into that some quantity of a rubidium azide solution. You dry it, you bond on the top window to seal the wafer, and then you dissociate the azide into the rubidium metal and nitrogen under the UV light. And then the nice thing here is that the more azide you dispense in, then the higher the buffer gas pressure in the cell, so we can make a few bars range of pressure just on the one wafer by changing the amount of azide in each cell. And we can measure the pressure spectroscopically, of course, from the broadening of the D1 line, and we can also measure the zero field resonance parameters like the line width and the temperature profiles of the transmission intensity after dicing. And we found out quite early in the project that the ratio of those two, which we call the sharpness of the zero field resonance, that's highly correlated with the sensitivity. So we find that the best conditions for magnetometry are when we maximize the sharpness. So you can see for this cell here, it's about 160 degrees C, where the line width is about 20 or 30 nanotesla. And so this is in the surf regime, where you have a higher atomic vapor density, and that suppresses the relaxation by the spin exchange collisions. Then the nice thing about these measurements is that the sharpness is easy to measure. You simply need to measure the zero field resonance curve. And so in principle, that could all easily be done on the wafer. So it could really streamline the fabrication process, because you could then know which cells in advance are going to be the best even before you dice the wafer. As I said, we don't actually test cells on the wafer right now, so we test them individually inside a magnetic shield, a few at a time, as you see in these larger oven units. And more recently, we started using this more fingertip size oven, and with these setups, we've been getting magnetic sensitivities which are around the 10 to 20 femtotesla root hertz level using our own control system. And so these validate that these cells are good for magnetometry. And so another thing about making OPMs mass producible then is not just the fabrication, but being able to relax the conditions on the operation of the OPM. And at the moment in MEG, that's really strict. And that's because although the zero field resonance design is very simple, as the name might suggest, then you always need to operate very close to zero fields. So typically within a fraction of the resonance width, or you lose linearity. And that's shown in these plots. So something like below 10% of the width and the resonance width, so sub nanotesla, along the modulation direction. And then in addition to that, then the sensitive direction of the magnetometer, or the pointing error, that depends on the direction of the bias field in the other direction. So you want to lie within this 5-degree contour of the figure, ideally. And that means we're talking about being within a few nanotesla of a true zero field in all three space directions. And to deal with that, well, usually you have compensation coils, both on the OPMs around the cell. These compensate small local field changes, and also wall-mounted feedback coils on the magnetically shielded room to compensate large global fields. And this is usually done, as shown here, with the help of some auxiliary or room-fixed OPMs like these. But arguably then, assembling 3 sets of coil loops like this around the cell is complicated. At least it's probably not something you could get a pick-and-place machine to do. So we tried to look for a better solution. So we developed this set of miniature coils, shown here in green. This is an XYZ set of coils where the current loops are all in parallel planes. So it's a biplanar coil, and it's made on a single printed circuit. And you have a few planes within the PCB, the different layers for each coil. And these simply get placed either side of the cell in order to work. And we really wanted to design these coils to be optimal for MEG. So apart from the geometric restrictions, then we wanted them to give better performance than, say, a triple Helmholtz coil or a cube coil. And one thing we want is a high homogeneity and high field region at the coil center, so that we can maximize the dynamic range. Well, maybe to tolerate porous shielding, for example, or even do away with those macroscopic coils. And we can get that, it seems, we can get that from these free precession signals, sometimes called FIDs. So we measure that the experimental field to current ratios are within 1% or so of the magnetostatics predictions. And then the spatial inhomogeneity of that field over the atoms we can estimate from this T2 star broadening of the FID, which is also on the order of %. And that's also agreeing well with the computed data. You can see that the field gradient is larger for Z, by the way, and that's really a deliberate design choice, so that we could prioritize a dual axis magnetometer where X and Y have the highest homogeneity. And of course, we're hearing a lot right now about tri-axis OPMs, and in those implementations, then maybe you want the broadening to be more equal, but you could design the coil differently. And also, we remember that we wanted a minimal stray field. So for us, we wanted less than 1% crosstalk at the typical sensor distance of standoff of around 20 millimeters. And the design said that we could do that. So this is somewhat true in practice. We can put a magnetometer this time outside the coils to measure the stray fields. This is your off-the-shelf keyspin sensor. And the shape of that stray field is roughly what you expect. The hotspots are a little larger, so about 2% is the largest defect. But it's very local, so with careful optimization, you could probably avoid that in a MEG implementation. And so that sounds like a really demanding specification, but fortunately there's a very easy way to convert that into the coil design that we ended up using. So there's a software package called bfield tools. It's in Python. And you simply program the magnetic field specification of your coil into that. and it will compute a set of surface currents that best approximate that field profile. And then you can convert that, you can discretize that and convert that into a PCB design file and then refine it as you like. So say if your specification is too aggressive, or the solution that it proposes is not feasible for manufacturer, then maybe due to overlapping wires, for example, and you can change it and iterate until you get something that works. And if you want the details of that, then you can listen to one of the creators of that software in this talk on YouTube. Okay, so let's conclude something. So for us, then, the main focus is to address the problem of making robust and reliable OPMs in an efficient way, so they can ultimately be used in MEG studies, clinical type MEG studies. Our next step is to focus on integration. So here are a few things that we've been working on, but we don't have published yet. The first is package integration into something small form that you can actually imagine on an MEG helmet. So here's a prototype produced this year by Megan. And you can hear about that in the poster session. And we've also been looking at vapor cells with metallized window coating, such as where you have traces for heating the cell. And we also want to explore vacuum packaging of the VCSEL and the MEM cell and do some closed loop tests where the biplanar coils are used to track the zero field. And then there are some other applications of OPMs like NMR and MRI. This is a proton FID that we've recently detected using our sensors, so we're going in that direction too. So with that, I thank you for listening to this presentation, and for the organizers for the opportunity to present, and of course everybody who took part in this work. It was a large and extremely enjoyable collaboration, and we're looking forward to where this sensor is going next. Thank you.